Okay, hi everybody. Welcome back. Part 2 of reinforcement learning. So let's get started.
Okay, hi everyone. Welcome back again. Let me just share my screen. Okay, so today will be an interesting session. Okay, we'll be covering what was also one of the landmark algorithms about in 2015. Okay, looking back, that's quite far actually. That's 7 years back. Okay, but back then, this was very popular. This actually inspired a lot of the latest models in reinforcement learning, known as actor-critic models. Okay, but the first version is like DQN network. Okay, this is for discrete actions, and this worked pretty well for a genre of games called the Atari games. Okay, so I'll show you some videos later. So this agent was created at DeepMind, and basically the idea is like a human. Okay, humans take in visual inputs like pictures, right? So this agent will just play from the pixels alone and then decide what to do for the game. Okay, and the main thing for this is that because they can use these neural networks to do functional approximation, it can work quite well for like very large state spaces like pixels. So imagine you have a game image like this. This is your game image. Okay, and then you process it through some network. Okay, later I will have a slide on this, like through some network like CNN. And then after that, you output an action. So essentially, this is the process. And because like you just put pixels here, it's very generic. You can represent like almost any game because anything can be represented based on pixels, right? So this is quite a generic architecture. They use it to play like all 57 Atari games that they considered. Okay, and like more than half were superhuman performance. Okay, but there were some that humans still do better. This is not the best architecture. Okay, in fact, there's no architecture that can beat humans at everything right now. Okay, it's still in research, but this was quite a big breakthrough back then. Okay, because it can play one AI, the same architecture can play many different games. Okay, so let's see. Okay, so these are some of the games that are played. The first one is Breakout. I believe I showed you all the video for Breakout last week. Okay, the other one is Space Invaders. Okay, if you're interested, we can actually go over to this blog to take a look. Okay, it's actually very similar to what you see here on the screen. Okay, so these are just two of the games that DeepMind actually uses to play their agents against. Okay, there are a total of 57 games. Okay, that was used. Okay, so this is something that I would like to touch on. Okay, last week I gave you a very brief overview of reinforcement learning. And this week, unfortunately, I have to give you all some math. Okay, if not, you cannot understand the how DeepQ networks work. So don't mind me. Okay, I will be stepping through this quite slowly. Okay, yeah, don't need to cry. Yeah, it's all right. So the main thing that you see here, everything on the right is the same. So now we have a very weird. Oops, sorry. We have a very weird symbol right now for our environment. So this environment will be basically like, you can treat your environment like an Atari game. Okay, like Breakout or the Space Invaders you saw the previous slide. Okay, this one basically is you take the environment and you give it an action, and the environment will then give you like what is the next output state, what is the next picture you will see. Okay, and then also it will give you a reward. Okay, whether or not you die or not, or whether you break some breaks and then you get some points. So similarly, your environment here will give you a state and a reward. Okay, so this state and reward are represented by S and R right now. Okay, so big S is like the total set of all states. Small s is like the current state itself. Same thing for action. Action is all sets of actions you can take. Like in the Breakout is either left or right. So this A is the entire big set of actions, and this small a is a specific action like left or right. Okay, this is some notation that is quite common in reinforcement learning. Okay, then next up we have this thing called the transition function. Okay, transition function is is basically very simple. Okay, given a current state, okay, and given a current action, okay, what is my next state that I will go to? So they call this usually S prime in the literature. What's the next state I can go to? So if let's say everything is deterministic, like if I do a certain action, my pedal moves to the left, right? The transition function will always be 1, okay? Because the probability that the pedal will move left when I click the left button is 1. Okay, but in some games, like if you play, I don't know, poker, yeah, sometimes if you were to like bet all in, okay, you may or may not win because it depends on what other people's hands are. So that one have a different transition probabilities for even the same action that you take, which is you go all in, you might win or you might lose. So there might be some cases where it's probabilistic. Okay, so this transition function will capture the probabilities of transiting from one state to another state, the current state to the next state. Okay, then this is, oops, sorry, then there's one last thing that is quite new here that I didn't go through last week. Next is this idea of a discount factor. Okay, so this is the idea, okay? In an agent that plays a game, okay, usually the game comprises of multiple steps, right? So step 1, step 2, step 3, as in time steps, you will see different images and then you give different actions. Okay, each of these frames sometimes come with a reward. Like if you break a block in like breakout, you will get some reward. Okay, so maybe this is a good time to go back to the previous slide so that you can see the breakout game. So you can see over here, you will get a reward when you hit the break, right? You see your score increases. So the discount factor just tells the agent how much to value future rewards. So do I want to be greedy and just optimize so that I get the most rewards in my current time step? Or do I want to plan ahead in a longer horizon and basically cater for rewards that I will get over the next few time steps? So the discount factor is like, you know, if you do investment, your discount factor is like your interest rate or something. So it's like 0.95, means your next state will be valued at like 95% the current state. So the next state will then be valued at 0.95 squared. So you can see that it gives lesser and lesser value to, so let's say your current state, this is the importance factor, okay? So you have an importance factor here, and then you have a state over here. So your current state, okay, will be given the highest importance factor, which means that I will value what reward I get on my current time step. But then for future time steps, they call it decay. Okay, decay means give it a lower value for the importance factor. So basically the rewards that I get in the future time steps will be valued less than my current time step. Makes sense, right? Because if you're an agent, if you get a reward now, it's certain. Okay, but in the future, it may not be certain because sometimes you may not get it. Okay, so the future rewards are more and more uncertain. So you don't value them that much. Okay, but if you want to plan for a longer horizon, you need to make sure that your discount factor here is not too low. Okay, you know why? Okay, let me ask you. Okay, if let's say I put my discount factor at 0.1. So if I do 0.1 like to the power of 5, is it a very small number? Okay, 0.1 to the power of 5 will be like this, 0.00001. Let me see, yeah, 1, 2, 3, 4, 5. Oh, wait, 0.1, 1, 2, 3, 4. I think I'm missing 1 0. Yeah, so it's like that. So can you see that if you put the discount factor like at 0.1, this will mean that I will not be like taking the value of the future states that highly. Okay, it will mean that I'm very myopic. Okay, I will only care about my current reward. Okay, so that's the idea of the discount factor, is how much to value future rewards. Okay, all clear so far for this discount factor? Okay, sorry for the math here, okay, but this is really needed for today. All right, so this idea of reinforcement learning, okay, can be modeled as like a Markov decision process, okay, which is what we saw last week. So this is a recap. So you all remember this Markov decision process? This is called the daily life Markov decision process. So each Markov decision process comes with a state that you are in. Okay, in this case, for DeepQ networks, the state will be a set of pixels. Okay, and then we have a certain action. So each state comes with a certain set of actions that you can take. Okay, each action will have a transition probability. Can you see that this is the transition probability that I talked about earlier? Given the current state S, okay, a certain action A, I will have a transition probability P, okay, which will tell me what is the probability I will get to the next state. So this new state, state 2, will be called S prime in the literature, which is the next state. Okay, and then this is my reward R. Okay, so actually everything is the same as last week. It's just that this week I'm giving you more of the notation. Okay, so all clear so far for this? So for certain states, like over here from state 3, you can have different transition probabilities because it can go either here or here. So over here, you can see that the probabilities are 0.5, 0.5. Okay, they must sum up to 1. Okay, you all know why? Okay, probabilities must sum up to 1. So this is one of the constraints for this Markov decision process. Okay, so let me ask you all now. Okay, I think I told you all the answer last week, so I see whether you all still remember. What if in a current Markov decision process, okay, your state right now, okay, requires a history of past states. Okay, what if, like, for example, a set of images for the game, like this is your game, this is like your pedal, and then your ball over here. How will you know whether the ball is going down or the ball is going up? Okay, can anyone tell me like a potential way to solve this? How can we make sure that, like in an Atari game, just given the pixels on that current frame itself, how can we make sure that we can capture like the motion of the ball? Okay, how will we make it such that the states are independent of the past states? Because Markov decision process, the states must be memory free, which means that they cannot refer to any past history. So anyone can tell me like how can we bypass this? How can we make it such that we can represent the Atari game as a Markov decision process? Any guesses? Okay, so you keep that thought in mind, okay? Because the answer will appear in the next few slides. Okay, just think about that. I'll be moving on. Okay, so I'll skip this slide first. I'll come back to it later. Okay, so the answer to that is actually this. Okay, so you can see that in this, okay, the state for the DQ network is actually not just one frame, but 4 frames of the game itself. Okay, so can you all see that in these 4 frames, you can see that this ball is here, then the ball move here, then the ball move down a bit, then the ball move down a bit. So assume that you are the AI with just these 4 frames alone. Are you all able to tell what is the motion of the ball? What is the velocity of the ball? If you think just from these 4 frames alone, you can tell the velocity of the ball, you just give me a thumbs up. Okay, so I think, Chicken, you gave a thumbs up. The rest, do you all think that if I give you these 4 frames only, can you all tell me what is the velocity of the ball? And I tell you these 4 frames are continuously linked. That means like, okay, y'all can see, right, that are you able to see that if we are given like a series of continuous frames, okay, we don't need any of the past history. This big thing can be considered one state in the Markov decision process. Okay, so our states here is not just one frame now. Okay, we are taking a series of 4 frames, and that is the state that we are seeing in the Markov decision process. Okay, are you okay? So each state is 84 by 84 pixels. Okay, the action is left or right, and the reward will be the total score. Okay, so let's go back again. Okay, so I just wanted to touch this for a little bit. So we do have this thing called Q learning, okay, which is basically, okay, given a particular state in the Markov decision process and given a particular action, okay, so we want to find out how good from this state, okay, how good this action is. Okay, so this is the traditional old way of doing things before neural networks, okay. What we will do is we will have this list of state action table, okay, which is also called the Q table. And each of these state action values will be mapped to a value. Okay, and this value is called the Q value. Okay, so using some reinforcement learning algorithms here, okay, mainly like temporal difference learning, okay, which is also similar to what we do in deep Q learning as well. So I will touch on what all this is. Okay, these are new terms to you. Okay, but I will touch on what all this is. I just want to highlight that in the past, what people do is that they have an array of tables like this. Okay, and then what they do when they read off a particular state and action, they read off this table. You know, it's like a dictionary. You read off the key, and then you get a value output here. So this was how it was done in the past. And can you all see what's the issue with this method of doing things? Okay, what if my state is exponentially, what if I increase my amount of states and increase my amount of actions? Do you all think that this table here is able to scale up if I increase my amount of states? Okay, so the answer is actually no. Okay, can't really scale up that well. Okay, because this actually scales up okay, it's actually polynomially in terms of state and action. The more I increase my state, the more grids in this table I will need, more memory space here. So what has been done to solve it? Okay, so the idea is actually using deep learning. Okay, you have one big architecture here. Okay, instead of doing like a fixed memory address, you take the state action and you get out the value. What we do is we feed in the state to the start of the neural network. Okay, and then what will happen is that we'll output the Q values for all the actions. Okay, so it's slightly different. Okay, I mean, you can also do the action here and then you feed in the action inside. Okay, but because of the way that this is computed, okay, it will actually be more efficient if we output all the actions given one state. Okay, so that we can make use of the same kind of structure for the neural networks. When we get one state over here, this structure here is all common. Okay, then for each of the action, you then just go into one node each. So this is actually a better way to do it by putting in the state and output the action. Okay, so this is a DeepQ network, DeepQ learning. Okay, basically takes in a state for your neural network. Okay, and outputs the Q values. Okay, so
I have a question. So the Q values here represent the next state or the action to the next.
Okay. So I didn't really explain Q values yet. So thanks for asking that. So the Q value is like that. You can treat it like this. So given a certain state, so let's say I have a state one, okay, and an action one, and I get a Q value of maybe 1. And then I get a Q value of like state 2 and action state 1 and action 2, and I get a value of like 0. So the Q value tells you how desirable taking a certain action is. So the higher the value for Q, okay, the more valuable the action is. So Q is actually, you can treat it as like a weighted average of all future rewards from that current state itself.
So that means that your diagram points to one node, actually doesn't point to one node. It points to all the green nodes, and then you figure out which action you want and then point to one node.
Oh, you mean the diagram down there, is it?
Yeah, this diagram.
Oh, it's actually you can ignore this part.
Okay.
Actually, this is just go straight here.
Okay.
Yeah, like that. Okay, any questions for this? If state holds 4 frames in the game, is the number of actions 4 in DeepQ learning? Okay, so Corinne asked this question. So the DeepQ learning, the number of actions there are depends on the game itself. So like the game of Pong, you only have left and right, and maybe the fire button for your ball. But for other games, like maybe you talk about what do you call that? The Space Invaders. You have left, right. You have a fire button. Maybe you have a bomb button. So it depends on the game itself. Some games have more controls. So there can be up to like 20 or 30. I can't remember the exact number for Atari games, but there can be based on the amount of buttons there are on the joystick. Okay, so there can be as many actions as that. Okay, but one thing for sure is that for DeepQ networks, the number of actions are finitely many, which is basically saying that it's not many. It's like within 30, within 20 is quite little. Okay, so later I will talk about like how this was extended for infinitely many actions. Okay, but one of the limitations for DeepQ network is that because of the way we need to structure our network to output all the actions here, we can only have finitely many actions. Okay, so that our network can actually be constructed. Okay, you cannot construct infinitely many nodes, you see. So this is one of the limitations for DeepQ network. But the idea is very simple. Given a state, it tells you the values for the next few states. And then what you need to do is basically, you see what value is the highest. Aha, this is my best action. Okay, because the Q values tell us the expected future rewards, expected sum of future rewards. Okay, So the Q value is like a proxy to how much more reward I can get from the game itself. So by taking a certain action, like for example, here in this on the left, if I take action 1, I get a total value of 1. Expected rewards will be 1. Okay, expected discounted sum, actually, not expected sum, expected discounted sum. Okay, but the idea is I will get, if I were to take this action, I can expect myself to get a total of 1 more point for the rest of the game. But if I take action 2, I can expect myself to get a total of 0 more points for the game, which probably means that you have died. Yeah, because this action 0 means no more points, right? Means you probably lost the game. So from this, you can see that you can just simply, okay, you can just simply just pick the action that gives you the highest points, which is QS1, A1, which is A1 actually. Okay, same thing for this deep Q network. When we do it, we can just feed in the state, and then we get a list of Q values for each of the actions we can take. And then we just choose the action that gives us the highest value. Okay, if clear, can you all like give me a thumbs up for this? Or you want to ask any questions? Okay, good. Looks like everyone understood. Okay, so what I want to do is actually, okay, I realize that maybe I should have put some slides in a different order, okay, so that I can talk about the Q values first. Okay, but no worries. If you have anything that not clear, please let me know. Okay, let's continue. So this idea of deep Q network comes from, like, this is the structure of the deep Q network. In the neural network structure, we have an input, a neural network, and the output. So over here, the input will be the image of your game. Okay, and you all remember the input here is not just 1 frame, it's 4 frames. Okay, and why do we need 4 frames? Because 1 frame is not enough to tell you the entire game state. You also need to take into account the velocity of the ball, the velocity of your bullet, or so on and so on. So the output will then be the state action values, otherwise known as the Q values. Okay, so this is in graphical form how it looks like, the game state. Okay, actually it's 4 pictures. Okay, just bear in mind, I put here 1 for space constraints, but it's actually 4 pictures for the Q network. We run through a neural network, and guess what? It's a CNN. You all remember CNNs? CNNs called convolutional neural networks. They are meant for images. Okay, and then next, we output a state action value. Means like from this state in yellow, what is the expected discounted sum of future rewards if I take action 1, action 2, or action 3? So anyone can tell me, okay, let's do a mini quiz. Okay, this is action 1, action 2, and action 3. If the neural network gives you these values, 0.3 for action 1, 2 for action 2, and -1 for action 3, what do you think is the best action to take from this state in yellow? Anyone can tell me? Okay, I see a chat. Action 2. Okay, very good. See, you all got what is deep Q network. Very simple. You basically take the state action values or the Q values, and then from these Q values, you just pick the action that gives you the highest value. Okay, so very simple. But now's the question: how do we train these Q values, right? Okay, if we have all the Q values already, then very simple, right? You just need to read off your neural network, and then you get your Q values. But unfortunately, this is not how things work. We need to train the Q values. Okay, and this is where, okay, I want to tell you how these Q values are generated. Okay, so before we go into the math, okay, I'd like to invite you all to think about something. Okay, imagine that you are in a maze on the left over here. Okay, you all played this maze before? This hatch maze. So you need to find your exit, the way to the exit. Okay, you all played something like that before? Okay, even if you haven't played before, but you get the idea. Okay, you have to get out of this maze over here. So you look at the diagram on the right over here. Okay, this is a happy face, and this is like a dead end. Okay, so imagine this is the goal. Okay, oh no, sorry. This is the goal. Okay, imagine this is the goal, and then the happy face is actually this is you. Okay, so this part is you. Okay, how do we want to learn? Okay, so that we can get ourselves to the goal, and then not go to this dead end. Okay, so very simple. So let's say in run 1, okay, I just randomly explore. I just go here, then boop, I go here. Oh, I get a score of -1 because this is a very bad situation to be in. I got trapped. Okay, so then when I do like some backwards learning, okay, this is actually called, so I can actually backwards learn, okay, this is a -1 over here. So that I can replay back my memory, like before I made that left turn, okay, what was the basically what was the state that happened here? So actually this state here can be like, you can actually then update this state, okay, with like a slight negative value as well, maybe like -0.5. Okay, because what happens is that I know that before I came to this state, I actually went through here. So here is actually quite negative as well. Okay, so in my second run, okay, I go through the maze again. I reach here. Okay, so assuming I don't do random this time, okay, by right, in order to get some experiences, I do randomly. But now I come over here. Okay, over here, this is an unexplored state. So this is a value 0. Here's a value -1. What will I choose? Will I go left or go right? Normally I'll go right? Because this is 0. Then I reach here, there like, oh my gosh, this is the exit, value 1. Okay, so I actually get, basically I get some reward from here. And then so when I do my like learning from this state, so this point here will be like a point of 0.5. Okay, because I reach this goal. Okay, but I have to pass through this state here to reach the goal. So this point here will be like a value 0.5. Okay, so actually you can average out these two values here. You get this state will be a value 0. Okay, so we can continue running through this. Remember last week we talked about Monte Carlo Tree Search, explore, exploit. So Q-learning also does very similar things in terms of explore, exploit. Is basically this thing called random exploration versus greedy exploration. So their explore is random exploration. So there's a fraction epsilon of the time, okay, where you will do a random action, and then epsilon of the time you will do a greedy action, which means you take the action that gives you the highest value. And then 1 minus epsilon of the time you will take a non-greedy action. So this is basically this random action. So this is actually very, very similar to what you all saw last week on Monte Carlo Tree Search. Okay, we actually have explore, this exploit, which is basically get the largest value, and this is the explore part. So the idea of Q-learning, after you do all this to explore the state space, okay, we not only do that, we actually keep looking one step backwards. Okay, in order to reach to this very bad state, what must you have passed through before? Then you basically update the value of the previous state and so on. So in order to do that, basically, you need to do something called temporal difference learning. Okay, but the idea is very similar. The idea is basically updating the future states backwards, so that your current state, you already get the value of your future states. So can you see that if you keep doing this backwards updating, eventually at the start over here, okay, if you keep doing this backwards up, eventually at the start, all you need to do is to do a greedy action. You just keep going to the place with the highest value, and then go to the place with the highest value. Okay, you will get to the endpoint. Okay, because the U that has gone to the bad place has feedback to the main route, okay, that this is a bad place. Okay, so you will probably not want to go here, but here you have no choice because there's only one way. But the idea of Q-learning is that because you experience something, you tell the earlier states what you experience, and then your earlier states will have some idea whether it's good or bad to go there. Okay, so this is the key idea of Q-learning, is this idea of backwards updating, okay, or otherwise known as temporal difference learning.
Let me ask a question about this. So can I assume that this sort of architecture is what the AlphaGo is constructed on? Is this AlphaGo's way of doing it? Because then my follow-up question is, how do you determine what is an action? Because an action for let's say Go, right? There's the board pieces, right? So you can put a piece. Do you assume that an action is putting one piece in this square and that is one action? Or is it another more complicated way of stating what an action is? Like, for example, if the opponent puts it in this square and then an action is putting it in the adjacent square, like what is an action in a game that is more dynamic?
I guess in this case, for your question on actions, it will just be the list of valid moves that each player can make. Yeah, so it depends on the game. So like in Go is one of the empty pieces on the board that you can place your piece on. If it's like a very interactive game, then it depends on what the rules are. So that is the action, and the state is basically the board game's state itself, like the pieces, where the pieces.
Right. Because like they can play Dota and they can play StarCraft, right? But the actions there's a lot of actions. I mean it's finite, but there's a lot. So does that mean that you just need to train like years worth, then you can get a good
Right. So
model?
for StarCraft, they didn't use Q learning because there's too many actions.
Okay.
They use a policy gradient method called PPO, proximal policy optimization. So that one is a bit more complicated, involves integration of some probability functions. Yeah, and then some information theory. So that will be a bit more complicated. I mean, if you're interested, I can cover that as well, PPO, A2C, but those involve quite a bit of math. Yeah.
So
But
we're talking about what is the number that we're talking about? Like roughly how many is okay for
based on my experience for Q networks, okay, if the number of actions is like below 100, still okay. Above that, good luck. You will take very long to train. Yeah, because imagine you need to train all the values for all the actions. Yeah, you need to back propagate all your action. It takes a while. Yeah, but if it's like small and finite, still okay. All right, but the idea of Q learning, you all can see, right, is basically you go to a state, you don't like that state, you tell the previous you, hey, don't come here. It's like a warning sign like that. You go to this -1 state, you tell the previous one, hey, don't go here. Okay. Yep. So basically from this, you can actually see like this is the idea of using what you have learned in the future to update the past. Okay, and that's really the main idea. And you asked whether AlphaGo use the same architecture. Very similar. Okay, just that AlphaGo doesn't exactly use temporal difference learning. Okay, they don't use like one state update before that. They actually learn the Q values using Monte Carlo Tree Search. So rather than just doing a one-time step update, they do the Monte Carlo Tree Search and then use the Q values, or rather use the value of all the states they have encountered to update that particular Q value. So it's actually more robust. It's not just one step. It's look ahead many steps.
Also, they actually sort of finish the game first. Then
not exactly finish, but they look through more states and then they average out the values of these states to update the Q value. So it is sort of like temporal difference, but it's not with a difference of one state. It's a difference of you average out. It's something like what do you call that, ensembling or something. Yeah, you basically average out all your what you have encountered in the future, and then that will be your value. So it's a little different from this DeepQ network. Okay, but what you said actually, you will realize that they actually combine back this DeepQ network with AlphaZero or AlphaGo, and then we form this thing called Mu0, which essentially is similar to what AlphaZero did, but with a single player mode using these Q values. So what you said actually can also be used to train DeepQ networks. Okay, but the architecture I'm talking about today is not the one using Monte Carlo Tree Search. Okay, so I can move on, right?
yes, please.
Okay, so this temporal difference learning. Okay, what is temporal difference learning? Actually, very simple idea. Temporal difference learning is like this. Okay, suppose you have an O value, okay, of your state, which is over here, QSTAT. Okay, how do I, and then I encounter this, okay, this is the temporal difference, or rather what I want to call this, okay, you can treat this as your future self. Okay, so imagine, okay, actually this is a very apt time to put the, Avengers, you have this Doctor Strange looking into the future, right? With that 1 million over 14 million possibilities, right? So the future self of you, okay, after looking into the future, then tell you, hey, okay, don't eat this chocolate. You have a tummy ache. Then you tell back your current self, oh, okay, I don't eat that chocolate. Okay, so this is like your future self telling you, that eating this chocolate here is not good. So you, after you tell back, then like, oh, maybe if you could do this in your life, maybe you will avoid some accidents. Okay, but unfortunately, we don't have this. But you imagine you can have a future self telling you how good doing this certain action is in the state. Then basically what we'll do is you add in the reward for that current state plus a discount factor for the next state. So you can see that this is the next state, st plus 1, which is the next state. After you take this state action, you'll get to this state, okay? And then what we do is we basically take the maximum of that future value, maximum action that can be possible from that future value, which is basically, we are saying that assuming that we do everything optimally for the next step, okay? This is my best value. This is my best Q value for the next time step, okay? So basically, you will know that if we take this value, okay, if we take this value plus this whole thing here, okay, this one is basically a one-step look ahead of the rewards. Okay, so it's actually more accurate because it tells you the current time step reward plus the expected future value over here. So you can see that this is actually a more accurate update than your current time step reward, right? Than this reward itself. Okay, because this reward is only looking at the current step. Okay, so basically we have a more accurate version of this thing to look forward to. Okay, we have a more accurate version of this. We have a more accurate version of the reward itself because we actually look ahead one step. And then what we want to do is we want to update this value here with that. Okay, with that value. Okay, but what we want to do is we don't want to update it fully. Okay, we don't actually say that, okay, it's equals to this straight away. Okay, because sometimes this might lead to some instability. Okay, because if you just change the value straight away, you might actually, what if this estimate is wrong, right? So we want to change it gradually. So we just subtract off this thing here, subtract off the old value, and then add a learning rate. So this is called TD learning. Okay, we slowly, assuming that this is our graph here. Okay, this is my Q, ST. This is my old value. And then this is my new value. The new value based on the one-step look ahead. Okay, rather than going to the new value directly, what I want it to do is I want it to go halfway like that. Okay, then this is the updated value. Okay, so can you all see that the temporal difference learning basically is just taking a step towards a more accurate estimate, but you don't take a step completely. Okay, because you're scared that if you go straight away to here, you might actually be estimating it wrongly. Okay, because if what if this value here is wrong, right? So temporal difference learning steps with a certain step towards what you think is correct. Okay. So actually this is quite cool because this temporal difference learning is actually what happens in the neurons in our heads. Okay, they have done some experiments. This is how neurons learn as well. Okay, by taking like a step towards the next most accurate estimate. All right. So now that we know how to get this, how do we get our experiences that we learn from? Okay, one way to get the experience to learn from for this Q learning is to actually generate all possible state action pairs. Okay, but you know that this is going to be very, very big. Okay, because there's a lot of states and it's impossible to generate all state action pairs. So what we can do is we can just basically learn from what is the most probable, what's the most common state action pairs. So how do we get what's more common? Okay, we basically do an epsilon-greedy policy. Okay, actually these numbers are a bit wrong. Okay, this should be epsilon and this is epsilon y minus epsilon. So basically epsilon-greedy means, okay, with epsilon number of times, I take the maximum, which means I take the action that gives me the highest value. Okay, and probability y minus epsilon, all the time I take any action, I take a random action. Okay, this means that most of the time, right, the actions that I generate, the series of moves that I generate will be more or less what is going to be more probable, because like you play perfectly or you play very well, you get this set of moves. And then you also give some room for exploration, okay? Because if you just keep doing what is best, right? It's like the chicken rice and the chicken chop story, like what I said last week. What you don't want to just keep eating the chicken rice because you think it's the best. You want to explore a bit with the chicken chop also. So this is the exploration. So let me just put here again. This is the exploitation. And this is the exploration. Okay, very, very similar to Monte Carlo Tree Search. Okay, so you exploit by taking the maximum Q value and you explore by taking any action. Okay, and in so doing, you bias the search such that most of the time you generate the entire sequence with what is the exploited action, with the max action. Okay, and some of the time you generate the explore action. Okay, and one of the beauty of this thing, Epsilon-greedy policy, okay, is like this. Okay, this is something that is quite common in the literature. Epsilon, okay, we start off with the value 1. Okay, and then through your experiences, you generate, it actually goes to a value very close to 0, which is like maybe 0.1. So you can see that as we do more, we call it like as do more simulations or do more runs, the epsilon will get generated from the value of 1 all the way to like a very low number, which means that at first we explore a lot, because at first we are not too sure about our scenario. Imagine yourself in like in the hatch maze again. At first you don't know where's the exit, so you explore everywhere. You explore, you see whether you can get out or not. After a while, you know the surroundings better and better. Then you try to exploit. You know that, okay, if I go left, it's a dead end. Then I won't go left anymore. I'll go right. I exploit. Okay, so this simulates this as well. So at the beginning, you're not too sure, so explore more. But towards the end, when you're more sure, you explore less. You exploit more. So this policy is called an epsilon-greedy policy. Any questions so far for this? Okay, don't worry, all this will be quite clear in the code that I'll run through with you all. Okay, so next up, how do we learn from experience then? Okay, so before that, this was how to generate the experience, okay? And we generate them using an explore-exploit approach. How do we learn from experience? Okay, so okay, in DeepQ network, we actually more or less learn randomly. So they actually have this thing called a replay buffer. So whatever you learn in the day or whatever you learn in your episodes, you store them in this buffer. And then maybe at night, then you learn from this buffer randomly, which is you choose particular experiences randomly, and then you learn from them. What do I mean by learn? By learn, I mean perform this temporal difference learning. Okay. So you can actually see that this is not exactly a very efficient way of doing it. Okay, so like for example, if you look at rats, okay, rats actually at night when they sleep, okay, I think it's in theta sleep or some theta wave sleep, they actually replay their experiences backwards. Okay, and then they can actually learn better from the experiences. So there have been papers expanding on DeepQ network to incorporate some prioritized experience replay that replay some states that are like the most surprising, that actually works better. But replaying it backwards like that actually didn't really work too well for the algorithm because of very high correlations in the states. Okay, imagine if your state and action is like giving you a very bad move, okay, a very bad outcome. Then you keep replaying backwards like that. All these states here will all be bad. Then in the future, you won't explore that anymore. Okay, that's not exactly what we want, okay, because we don't want to limit the exploration. So doing this actually not that great for DeepQ networks. Okay, but I'd like to show you all this video. Okay, so this is a video of hippocampal replay. So, okay, can you see the screen? Okay, so this is a real rat, okay, running through a maze, and you can see that they actually put an electrode in the brain. Okay, it's a poor rat. Okay, the electrode is actually live when it's alive, is still in the brain. Okay, so you can see that these are what's happening in the, they call it place cells in the rat. You can see that as the rat goes through the maze, certain parts of the brain are actually activated. It's quite amazing actually, because based on the patterns of activation, the researchers can actually trace which part of the maze the rat is, because each part of the maze have a different set of activations. You can see by the different colors. Okay, so that's more or less it. The main thing you can see is that the, oops, okay, let's stop this. That was scary. Okay, let's go back. Okay, so the purpose of me showing you this video is that actually for people who have done this kind of brain research, it's been shown that what you have seen in the previous slide here exists. Okay, we actually do this kind of experience replay for mammals, even for humans also. There's this form of experience replay where we learn from what we experience in the day, and then at night it consolidates and we learn better. So this DeepQ network uses a bit of this biological inspiration in order to do this replay buffer and then learn from experience. Okay, it's quite important. Okay, so that's why if you don't have enough sleep, actually you find it very hard to learn a new skill. Okay, because actually when you sleep, you consolidate your experience, you actually replay some memories in your brain, you strengthen certain connections. So sleep is important. Okay, so for those who like to just drink coffee and not sleep, like in the earlier Markov decision process, okay, it's not a good idea. Okay, we actually have quite sleep is actually quite important, okay, for learning. Okay, so you can treat like DeepQ network as like in the sleep phase, it samples, okay, it randomly samples from the experience replay buffer and learns a more accurate estimate of your Q values. Okay, so this is the equation for Q values. Okay, so I realized I should have put this slide earlier, but the idea is Q values measure how good an action is at the current state. Okay, the higher the better. Okay, this equation at the top, okay, you don't have to worry too much about it. I'll explain it in the next slide. Okay, each state and action has an optimal Q value, which is basically this optimal Q value means is the trained Q value. Is like it's already learned. Okay, so the update of this optimal Q value is done iteratively. Okay, by taking into account the next steps S prime and A prime, given current steps S and A. So this basically what is trying to say is that it's like doing this is basically updating, okay, in the most updated values Q star would be equals to the expectation of all, okay, of all future states S prime. Okay, we take the value of all future states here. Okay, this means that we also weight according to the transition probabilities of all future states. Given the current state and action, what is the value of the next future state? Okay, plus the reward at the current state. So essentially what I'm saying that if this is already well trained, this, okay, is none other than saying this is the expected future sum of rewards. Okay, I would like to put here discounted sum of rewards just to be precise because of this gamma discount factor here. But you can treat this Q, okay, if it's well trained, okay, we call it Q star. Okay, it means it's the expected future discounted sum of rewards. It's basically when you get this Q value of that certain state, you already know what reward you will get at the end of the game. What is your expected reward, or what is the like average reward if you play many times. Okay, so sorry about the math here. Okay, but this Q this Q thing is quite important to explain. Okay, so how do we learn these Q values? Okay, so earlier you saw that in the temporal difference learning, we step from the old value to the new value, right? Okay, so in neural networks, it's a little different. Okay, we don't really have the opportunity to do this thing here. We don't really have this opportunity to do this thing here. Okay, because there's just too many states and too many actions. Okay, in order to do this update here, right? If you were to use temporal difference learning, you need to step through all possible future actions. Okay, over here. Actually, no, this we can still do. Okay, but the thing is, if we were to do the update the traditional way, okay, when we update the Q value here, we actually need to step through all the future states that is possible. Okay, which is actually can be quite large. So instead of doing this update, which will require stepping through all the possible states, okay, what we do is we use a loss function, and the loss function is very simple. It's just basically the mean square error, okay, between the actual actual value and the predicted value. Okay, and in this actual value is actually the one step look ahead value, and this is the predicted value, which is the current based on the current state and action. What is the Q value? Okay, so we basically learn to minimize the mean square error between predicted and actual. Okay, and then we also use a replay buffer, okay, which samples randomly. So this is the more in-depth thing. So you can see that this yi is actually this one step look ahead. thing here that you can see. Okay, there's one extra thing to take note of. Okay, is basically that there's a need to use a previous network instead of the current network. So you can see that over here, this is theta I minus 1, which is the network at iteration I minus 1, the previous time step. And then this is network at theta I. Okay, we don't use here to be theta I because if you use this to be the same, okay, there will be an issue about like chasing the tail like that. Like you have a certain target that you want to hit. So imagine this is your predicted target and this is your actual target. And your actual target is also using the same network as your prediction. So you are actually like chasing your own tail because your target keeps moving as well. You want your target to be fixed so that you can step to the target. So that's why we need another network. Okay, we need a target network that is fixed. Okay, so that we don't have a moving target. You know, if you have a moving target, it's very, very hard to hit the target. You step towards the target moves. You step to the target moves. So in order to make sure that this doesn't happen, we have a fixed network called the target network. And so after some iterations, we then update the target network to be the same value as the policy network. So can you all see that this is very, very similar to AlphaGo? AlphaGo also has a student network and a teacher network. So this is very similar to that.
But at the time of the update, doesn't then the policy, the training network equal the target network?
It does, it does.
Yeah.
So because it's supposed to, this idea is called bootstrapping, which is basically you move your estimate towards a more accurate estimate. So both are estimates. Actual and the predicted are both estimates. You don't have these actual values. Unlike supervised learning, your actual values are not really given. So you need to like sort of estimate your actual values as well. But because you fix your target network, and then you step your predicted networks towards the target network, and then when you update again, okay, your target network will actually be more precise. Because remember, your predicted network is updated to the one-step look-ahead values. So it means that once I update the target network to the policy network's weights, if all goes well, my policy network will already incorporate, my target network will already incorporate the one-step look-ahead values. Then if I have a one-step look-ahead value, I do this again, then it's like equals to two-step look-ahead. Then you do again, it becomes three-step look-ahead. So it is going to a more accurate estimate if we keep doing this algorithm again and again.
So can I say that a run through or flow of how this works is you have two, you initialize two networks. At first they will both be the same. Then you do one state, you feed one state. And then the one that you're training on looks at the output and then compares it with the one that has not been updated yet, and then keeps doing this until maybe like 5 steps or 10 steps, whichever you code, and then you update the holding network. Then you continue to train the training network again until the next time that you update the holding network.
Correct. So your training network is the policy network and your holding network is the target network. That's correct. And bear in mind that this target network is actually the one-step look-ahead value. So it's actually quite an ingenious way. We are updating our estimates to the one-step look-ahead values. And then after that, we sync up so that the one-step look-ahead value, this neural network here, is actually the one-step look-ahead neural network, which means that we get more and more accurate estimates. Yeah, so that's the idea. Okay, this is a very important trick, okay, because even in policy gradients, they use the same technique as well. Very, very similar technique. Okay, how do you prevent chasing your own tail? You fix your tail. Then when you move very close to your tail, you then update the tail again with the new position. So at least when you're training towards the tail, you don't zigzag, you go straight to the tail. Okay, but then this tail can move again. Then you go again. Yeah, so the idea is this is quite a common idea in deep learning. Even for GANs, they do something similar also. Okay. Because GANs also the target keeps changing. Your discriminator and your generator keeps updating their parameters. So you need to fix one of them in order to train the other. Okay. So how do we visualize Q values? So this is the game called Sequest. So you can see that this frame on the left here is frame A. You can see that this ship is just randomly moving around. So it's but it's on the same, this submarine just came out. Okay, so at this point A, the reward value shot up. Okay, it means that because your submarine is the same height as this enemy, you can actually destroy this enemy if you fire a torpedo. So the expected future value went up because there's this possibility of you being able to fire. At state B, you already fired your torpedo and your torpedo is about to hit the submarine already. So this is the highest value because immediately after you are going to get the reward for destroying that submarine or destroying the enemy. After you destroy the enemy, your next state is C because there's no enemy to kill. Okay, and this expected future value reward drop down. Okay, it doesn't mean that it's a bad state. It just means that the reward has already been claimed at state B. Okay, remember Q values is the expected future discounted values, right? So whatever rewards you already collected doesn't count anymore. So we only care about the future. So the Q values only care about the future. It doesn't care about what rewards you got before, which makes sense because like imagine if I were to ask you, what move to play in a Go game? Do you care about what are the good rewards you got in the past? You don't really care, right? You only want to win, right? So you only care about the future. So this is something quite important. All right, so how do you choose the optimal action? Basically just choose the maximum action, okay, out of the neural network's values. So the neural network will return you a Q value for each action. You just pick the action with the maximum action. Okay, so one of the key insights of deep Q network is you can approximate this very, very large state space of QSA state space with the neural network. And this allows you to do on bigger and bigger state spaces. Okay, how to improve DQN? One way is to incorporate some form of planning, because right now deep Q network is just basically doing a random network selection or greedy selection, but it's only for the current move. So if you can do some form of planning, okay, you can actually improve the performance. Okay, so you can use like Monte Carlo Tree Search to do planning. Okay, and if you do that, you'll get something like mu0, which basically does that. They use Monte Carlo Tree Search for planning over this deep Q network. Okay, you can also apply the continuous action spaces. And how do you do that? Okay, because if you will have to have a separate Q value for each of the actions, you will have infinitely many action, and that's not possible in neural networks. So what you do is, instead of using the Q values to choose your actions, you have a policy network. Okay, this is a different policy network from what I talked about earlier. This policy network simply, okay, gives you the action to take given a state. Okay, so basically this action can be a continuous value. And so you can apply this to continuous action spaces because you have a network to tell you what action to do for each state. So this kind of methods are called policy gradient methods. So policy gradient methods is basically what I talked about last week. The methods available are like PPO or A2C, A3C. Sorry. All these are quite popular methods. All right, so enough said. Now in the last 5 to 10 minutes, I would like to basically go through a notebook to show you how DQN works. Are you excited to see how it works? Okay, so let us use this problem as an example of how DQN can work. Okay, this is called the pole balancing problem, okay? Do you all think it's difficult to balance a pole on your hand like that? Yes or no? Okay, so, okay, who thinks balancing a pole on your hand like that is difficult? Raise your hand or like put a thumbs up or something. Yeah, who thinks balancing like that is easy? Okay, so very good in good hand-eye balance. Okay, hand-eye coordination. So we have this environment called the cut pole environment in reinforcement learning. It's a very classic environment for like beginners actually to balance a pole on a cut. Okay, and you'll be surprised how difficult it is to let the AI learn. Actually, deep Q networks take quite long to learn as well for this. So we have this cut position, velocity, pole angle, velocity as the state space, not images. Okay, we just give this, or you can also give images also, but in this example, I only use this 4 values. Action is either left or right, and the reward is +1 every time that the pole is balanced. Okay, so let's go to the notebook for the last like 5 minutes, 5 to 10 minutes. Hang on. Okay, can you see my Jupyter notebook? Okay, so this is called the couple problem. Let me just run all. So this is the state. We have a cut position, cut velocity, pole angle, and pole velocity. Okay, and then basically we have a reward, and basically the starting state is a random state based on all this here. So you lose the game if the pole is more than 12 degrees away from your vertical, cut moves more than 2.4 units from the center, or okay, you actually win if the episode length is more than 500. So basically we install some prerequisites. Okay, so this one is a notebook that I actually created to show this environment. You can actually see a very cool video of the environment moving. So let's take a look at this. Okay, so this is done using this thing called OpenAI Gym. Okay, OpenAI Gym is a, let me just show y'all, maybe OpenAI Gym. So it's a place where you can get like all these environments. You can get Atari environments here. You can get like classic control environments like mountain car, couple. Yeah, you can get all these environments over here. So you can basically do cool stuff here. I myself actually am learning some way to interface with this software called Unity. You all heard Unity? Unity is the game engine. So in Unity, you can also sync up with Python and do this kind of reinforcement learning stuff. So that's actually what I'm intending to do next. Okay. So this is the way to visualize the environment. So I created this. Okay. I'm not going to go through this code, but this code just basically shows you the environment itself. So this is a random agent. You can see that it dies after 11 time steps. So you can see the actions in this environment. So we have only two actions, either left or right. Action left is 0, action right is 1. Okay, we have the state. We can print out the state here to be like that, 0 point whatever. Yep. So these are the 4 values that we have. The pole velocity, pole position, cut velocity, cut position. The reward is a 1 if you still survive, and is a 0 if you die. Okay, and done basically is whether or not you die. If you die, is true, or if you have exceeded 500 episodes, then it's true as well. Info can disregard for this environment. So how good can human expertise help with this? So I give you all this example, okay? So if let's say I have a pole, okay, like that, a pole falling down like that, and I have a cut over here. In order to balance the pole, should I move my cut to the left or should I move my cut to the right? Okay, you all can shout that answer, left or right. If the pole is going to fall like that, should I move my cut to the left or my cut to the right? Okay, can type in the chat also. Left. Okay, very good. So exactly. So this is the intuition that we do. If the pole angle, okay, is less than 0, is the pointing to the left. Okay, then we move the cut left. If not, we move the cut right. Okay, so let's see how good this can do. So you can see that it died after 47 time steps. Okay, so just using this very simple approach, not enough to solve this problem. Okay, then what if we do like more things? Okay, we also do velocity. If the velocity is to the left, we also move the cut to the left. Okay, and then we can see that, oh, not too bad, 250. Okay, but you can see that it still cannot account for the problem of the cut going off the screen. Okay, it balances the pole, but you need more than this to make sure that the cut doesn't go off the screen. So you need to add more if-else statements here to say that if the position is beyond a certain thing, then let the pole go to the other side and so on. So you can solve this using if-else. I think with like 5 or 6 if-else statements, you should be able to solve this fully. Okay, but this is actually easier to solve with if-else than with a neural network. Okay, I tried very long to get the DeepQ network to work actually. Yeah, although this is a very simple environment. So it shows that DeepQ network can be hard to train. So let's do the DeepQ network. We use this loss function, which is the mean square error. And we basically do, this is the target, Q reference the target, which is the one step look ahead by the target network. And this is the policy network. So it's the same as what I did in the slides. All this you can just take a look. Okay. So one thing that I didn't do is I didn't use mean square error. Okay, because mean square error actually is quite what do you call that? Has a very high error towards the edge. Okay, because it's an exponential increase. So I use this error called the Huber loss. So you can actually search Huber loss. Huber loss instead of doing this quadratic curve, beyond a certain point is actually a linear line. So actually it is more stable for training. So if you all want to use stuff to do like mean square error for regression problems, try out Huber loss. Okay, Huber loss is actually better in my opinion. I've used it for a few instances, and I think Huber loss is much better than mean square error if you have very large values. Okay, that's my own take on it. Okay, so the replay buffer is basically to store the input samples, and then we randomly sample to learn. So it's like we replay our experience in the day now and learn from them at night. So this is the code. Okay, we use TensorFlow to do it. Okay, these are the hyperparameters to do. Okay. Then I actually shape the reward for this, because if a reward of 1, it leads to very high rewards. Okay, so I actually like divide it by a certain value to like try to make the reward a bit lower, try to cap it between like -1 and 1. Okay, over here is actually -1 and like 5. Okay, but we need to reduce it so that the network can learn better. Okay, this is the initialization. We initialize the policy and the target network, a loss function optimizer. And then if there's a file already there, we then load those files, which is the network weights. Okay, right now I don't have a network weight, so it's learning from scratch. Okay, but if you have a network weight, you can load it. Okay, get model is basically just do a sequential model for observation space, hidden layer of 1 to 8, and then like a dense of like the action space, which is like the number of actions. So this gives us action space number of outputs. So this will be like your Q values. Okay, update weights is the way to update our target network to make it the policy network. So you can see that we take the weights from the policy network, and then we update the weights to the target network. Okay, remember is to add an episode to the memory, state, action, reward, next state, done. Okay, self.memory is basically the memory we have, and then we only store memory size number of memories. Okay, to act, basically if it's below the epsilon, which is exploration rate, okay, and it's not a greedy action, okay, we randomly sample. So basically if we, so at first, okay, our epsilon over here will be like, okay, so in this case, we explore fully at the beginning. Exploration rate is only 1. Okay, and then towards the end, we will then do the greedy action. This is the greedy action, which is basically we take the Q values, and then we choose the maximum Q value. The experience we play, okay, this part is a bit complicated. Okay, I'll just be stepping through briefly. Okay, so we basically randomly sample all this from the memory. Okay, we predict the next sample for this one, future rewards. Okay, this is the target network, and then we basically do this one step look ahead, R plus one step look ahead. Yes, this is the same as the equation earlier. Okay, and then after that, we only do for the updated Q values the action that we chose. So we do a one-hot encoding mask, okay, in order to like multiply it so that we only backpropagate the gradients with the actions that we chose. Okay, then we also do the current step look ahead with the policy network. Okay, and then what we do is we'll apply the gradients to the policy network. It is a bit complicated, okay, because this is not using Keras. Okay, we can't really use Keras for this. Okay, so this is actually using the TensorFlow itself. So this is a bit more complicated. Okay, but the idea is basically to do this.
So you said to take a random memory. Why do you take a random memory?
Okay, because we don't want to take the memory of the last few episodes fully, because then there will be very high correlation. And if like it's a bad outcome or a good outcome, all the states that you experience will all be labeled bad. We want to like randomly sample so that the chance of us getting more than one possible outcome is higher. Yeah, if you would update your states in this like very linear fashion, you will realize that you might bias your search towards based on what you search in the beginning. If let's say you search something good, you might just keep going to that good place. You may not explore enough. Yeah, so the replay buffer actually helps to ensure that you have sufficient exploration and you average out the value of your states with more experiences rather than with just that one experience that you have.
So this is a technique that you use throughout any of the games that you play, like a replay buffer to not, so
it's to prevent high correlation between your states.
But this is only for this random sampling of the memory is only for the target, the two networks, right?
The policy network.
The policy network will be give fed with a random sample, whereas your target network is the one that the state in which it is in right now.
Oh, no, 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 no. Both the target and the policy network will be fed the same samples actually.
Oh,
Yeah,
oh,
it's just that
so
we only train the policy network.
so when you're training is when you feed random samples, um, and it's not like you are actually having the card and moving. You're just training it based on a snapshot in time. The next snapshot could be a totally different uh, state, like nothing to do with the previous state.
Yep, yep.
Oh, but only when you are actually playing the game, then you continuously feed the state next state.
Correct. So this replay buffer
Oh,
is basically what you have experienced before, and then you just take a sample and then train it. So actually, if I were to draw the diagram, this is like your state. Can you see my drawing? So imagine your state actually transits to like 3 other states with certain probabilities. Okay, so by having a replay buffer, it's like saying that, okay, I give the chance such that maybe I can sample like with respect to my expected probabilities with a higher chance than if I don't. So if let's say, so there's no problem if the environment is deterministic. Okay, then you don't really need a replay buffer. Okay, or actually in this case for like for Atari games is actually deterministic, but you still need a replay buffer because if you were to just bias your search according to what was initially good or initially bad, you may not explore enough. Yeah, but the idea of this replay buffer actually works more for like if it's probabilistic like this. Okay, if you were to just train backwards like this only, you will realize that you actually bias this node. Maybe this is a very good value, but then most of the time you'll experience a very bad value here, but you just don't get this transition. So you might actually think that, oh, this node is very good.
so it's to force the network to look at the options in which it may not have gone to.
Yeah, so if you do a random sample, maybe you can sample all this as well,
Okay,
rather than just having that good state. Because you can see that if you do a if you don't do random sampling, and this is the only experience you have experienced, you might just keep deluding yourself into thinking this is a good state. Yeah, so by having some random sampling, you might cause it to be less correlated, and you might be able to learn the other like outcomes as well.
so actually you play the game many times to get the memories, to get the snapshots of the memories and the outcomes. Then you train it. So it's not actually training when you're playing the game. You play
Yes,
the game first,
you play the game, then you train later.
play, and then you train later. Oh,
So you highlighted one of the more one of the reasons why DQN is like not that great. Okay, it takes a long time to train. So like to train the Atari games, actually it takes about 3 days to play one breakout game. Yeah, so that's why the notebook is not on Atari. Okay, because that one will take 3 days to run. Wait, hold on for a while. Okay, yep. So I've actually run this code live. Okay, just that you couldn't see it. It's over here. So we run for like 100 runs, and then we just see basically if we have enough memory, we do the experience replay, and then after that, while we gather memory per run. Okay, so over here I just put as 1 to make it faster. Okay, so we basically at each step we just store the transition into our memory. Okay, and then what we'll do is we then basically update after a certain number of runs, we update the target network. So you can see that this is the results. Okay, it's not too bad. It's like about, you can see the exploration rate is going down as we train. Okay, it means that we exploit more and more. And towards the end, you can see that this didn't train that well. Okay, this went up to like 129, 120, 199. Okay, so sometimes it's based on luck because we randomly sample. So, okay, so over here, you can see that this should predict left. And then indeed, this Q value is higher. Also, this is actually the output of the DQ net. So the left one is the Q value for the left action, right one is the Q value for the right action. Here we should predict right, and yeah, this is higher than here. So actually this is okay. Okay, then let's visualize the agent to see how good it is. So this agent, not that great. Okay, we can train this some more. Okay, but due to lack of time, we won't do it. Okay, I'll just load in like maybe the train weights that I've done earlier today. Okay, just to show you all like how if you run this enough times, okay, you can actually you can actually get a better performance. Okay, so it's like that. Wait, sorry, I think I need to probably reinitialize it. Okay, let me just reinitialize and just stop this. Okay, so I think this should work. Oh, okay, it crashed. Okay, but either way, the idea for this DeepQ network is that you have to just learn more, and then when you sample your transitions, and then you will get better. Okay, but it might take a while to learn. So this is not the most this is not the best model, but this is one of the foundational frameworks that inspire a lot more models later on. Okay, so later the most common models that I use will be called the policy gradient models. And I tried the policy gradient model on this couple. You can solve it within like 10 seconds. So it's a huge difference. So DQN is not very efficient, but the idea of this replay buffer, the idea of doing this Q value updating with temporal difference learning, these are ideas that are used in the literature as well. Okay, if not, actually, yeah, I'll stop my share here.
Okay, thank you very much.